Come on, Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
Time for a pop quiz. Huh, nicely integrated.
It's 5 o'clock somewhere.
Hello everybody, welcome on in. My name is Pen Center. We are here today for day 3 of machine learning. We're going to pick up where we left off, doing a little bit more classification and seeing what kind of stuff we can chat about today before I have to head over to the brewery. My shifts got switched. So rather than working the opening shift and streaming this evening, I have to stream this morning so I can work this evening. Yeah, so this is the Friday stream. I owed you this from Friday. This was our machine learning stream set for Friday. But I wasn't super feeling up to doing anything on Friday. I also know it was July 4th for a lot of people. So I think it all worked out well anyway. So welcome in, Jeff. Welcome in, Martin. Hi, Phobos.
Rest is crucial for recharging those mathematical muscles. Dream
Hi,
of
show.
theorems and be ready to conquer the day.
Hi, Sasha.
Sleep well and
Hope
see
you're
you
all
on
doing
the flip
well.
side.
Frickin' show. I missed you. So we had started into the classification chapter, which was chapter 3 of the Reese textbook. We were looking at KNN clustering. And Reese had us upload the, what was it called? The diabetes data set. So we looked, they kind of did an overview of KNN, which was this idea of looking at the data points. So we're trying to classify an incoming data point. We're looking at the surrounding neighbors, and whichever one wins, I guess, like the democratic vote, whichever color or cluster wins, that's how that new piece of data X here gets assigned. So it is dependent on the clusters, I assume, right? So it is dependent a little bit on the set of data that we give to the model to make the initial clusters. And it's also going to be dependent on our choice of K in this case, which is the number of elements we're going to look at. So there's a couple things it is dependent on. So all of that introduction I was comfy with because I'm semi-familiar with KNN. We were looking explicitly to, maybe I'll just blow this up so you can see it a bit more. We were looking at the MLR library. So we did have to download that. We opened up MLR and Tidyverse. This is just all the information about how to get some of the original plots, which I don't think is that big of a deal for us. And then this was the big thing, using MLR to start creating a model and start basically creating a script that we can upload to Discord in case you want to play around with this in R. So Reese had broken this down into 3 stages. We had to define the task, define the learner, and to train the model. Reese tends to use tibbles, so when we were working in R, everything got uploaded as a tibble. So we brought our data in, we converted it to a tibble. All of this is just ggplot stuff we don't need. And then we went ahead and defined the task. So let's see if I can remember what this stuff means. So, I mean, this is our label, right? So the diabetes task is our label for the list that's going to pop out. And then we had make classification task, I guess, is the function. We input our data as the tibble, and then the target, it must be the variable that we're looking at. So class inside of the diabetes data set must be the one we're looking at. Yeah, so class is the factor that we're looking at. It wouldn't make sense to do KNN for the other 3 because they're numeric. Sorry, you probably just heard my phone go off. Do that. So that's what I assume the target is doing here. So we're saying we're going to do a classification task. We're going to input the diabetes tibble, and the target's going to be the class factor. That's true. It was the 4th of July for everyone. Yes, that is true, isn't it? It didn't feel like a holiday for me, that's all. My holiday was Tuesday. KD tree stuff? I don't know. What's KD tree? KD just reminds me of craft dinner. So the second step was to define the learner. So define the task, meaning, I guess, what kind of task we're doing. So like defining classification. Defining the learner must be the subgroup of the classification task. Would make sense to me, right? So make learner. We're telling it it's KNN, so classification KNN. So what is this? PAR vals. So we're telling it to do K is equal to 2. So 2 clusters. Is that true? Maybe I should quickly just look at this one more time. Okay, so defining the task. It does go through some of the things here, right? Yeah, so make classif task, make regression task, make clustering task. So it's just, we just have to tell it what kind of class to do. That's fine. Right, so the learner is telling it which algorithm to use. We're in classification, and we're telling it to use KNN. What are the parameters, though? The argument par.val stands for parameter... Oh, just parameter values. Okay. So the only parameter KNN really needs here is the number of clusters, and in that first step we gave it 2 clusters. Okay, cool. Actually, I should probably rerun these because we don't have them in the environment. And then I remember what we did is we trained the model, and then we took a look at how things looked, but we used the original data. And just let me remind myself, was it the full data? I think it was the full data, right? We gave it the full data to train, and then we went back and looked at how well it did on the full data. And then looked at the performance metrics. Now, that was a silly thing to do because that would have probably overfit the model, right? It'll overfit the model, and I think the main issue is that, like, we never really got to classify it using data that the model hadn't seen yet. And so that was the big problem we ran into, was we got these really high... do I have the KNN model? Yes. So this is the prediction, and we can look at the performance. Our performance is like a 70%, sorry, it's about a 7% MMCE, so that's, what is that? Something... This is like a mean error of some kind, right? And this is the accuracy. Our accuracy was like 93%. So, like, fairly high. What's the MMCE again? The mean misclassification error. The mean misclassification error. So these are opposites of each other? Do these have to sum to 100%? It looks like it. Kind of looks like it. Hello, ICUP. How are you doing? Happy Sunday to you. All right, so that was kind of the issue there, right? We don't want to train using all of the data, and then, because then we're going to be unsure about whether or not it's going to be a good model for data that hasn't been seen yet. So we talked. The book talked a little bit about this Bayes various trade-off. And one of the things that we want to consider here is doing some kind of cross-validation technique in order to see if we're overfitting or underfitting. So we started looking at, I think, holdout cross-validation is what we looked at first. And I assume we'll maybe go through the other two as well in this chapter. And this is roughly kind of where we stop. We stopped somewhere here in the holdout cross-validation process. So let's remind ourselves blah, 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 holdout. So the holdout is this idea of breaking up the full data set into a training and a test. So we saved some proportion of it as the testing data, and then we use that testing data to see how good the model is at predicting using that original training set. And so that's kind of what we were doing down here. So let's see if I can remember what was going on. So this is just the label. Make resample description. Okay. So method just is the type of cross-validation we're using. The split is the percentage. And the textbook had suggested a 2/3 split. Stratify. What the heck is that again? What does stratify mean? I've included an additional optional argument. Stratify equals true. It asks the function to ensure that when it splits the data into training and test sets, it tries to maintain the proportion of each class of patient in each set. Oh, so it's about making sure that our population sizes are roughly the same. So it's a representative sampling. Okay. Could that be a bad thing? Could that ever be a really bad thing? Or do we always just want to use stratify equals true? I don't know I'm learning, guys. I don't know the answers to these questions. I'm just throwing questions out there. If you have answers to questions, you're more than welcome to post them into the chat. So we did a holdout cross-validation here. We did a second holdout cross-validation using a different split. But I'll put the first holdouts into the environment in case we need them for something. Okay, so we did exercise number 2. So this is where we got to. We got to creating a confusion matrix. Okay, cool. I think even the attempt to avoid bias would probably introduce a bias. Yeah. Isn't that the fun part about statistics? Every time you try to remove a bias, you maybe inadvertently also include a bias somewhere. Nothing is ever bias-free, right? I think that's the key takeaway. So what do they mean by a confusion matrix? I feel like I've used a confusion matrix to classify false positives and true negatives. So these are like type 1 and type 2 errors that we would normally say in like statistics class. I believe that's what a confusion matrix is. But let's see if that's the same here. We have 3 classes. How many classes do we have? So it's probably going to be dependent on the number of classes we have. So there's 3 different classes. So our confusion matrix will probably be a 3x3, right? It'll be how many of factor 1 were classified as factor 2, how many of factor 1, how many were correctly identified, how many were identified as factor 2, how many were identified as factor 3. So it's the diagonal. Usually the main diagonal tells us the information that we're curious about, which is how many of factor 1 were correctly classified, how many of factor 2 were correctly classified, and etc. That's how I suspect the confusion matrix is going to look, based on some of my experience, but let's see if that's the case. Tabular representation of the true and predicted class of each case in the test set. Perfect. With MLR, we can calculate the confusion matrix. Oh, it actually has a... Oh, that's nice. We don't actually have to code anything. It's already pre-programmed as a function into the MLR library, so that's cool. Calculate confusion matrix function. I mean, that's a long-ass name for a function, but it works. The first argument is $pred. What? Of our holdout CV object. Holdout CV. Oh, this is how R deals with finding something in a list with the $sign, right? Is that how this works? Holdout CV. Yeah, okay. So it's going to dive into this particular list. It's going to go into the predictions and grab this information. Okay. Yeah, $signs are weird here. But I see what it is. So it's going into that particular list, finding the predictions, and doing something with it, right? So this is the input that function needs, all of the predicted values. Holdout CV, which contains the true and predicted classes of the test set. The optional argument relative asks the function to show the proportion of each class in the true and predicted class labels. What? Asks the function to show the proportion of each class in the true and predicted class labels. I don't know if I understand that sentence. I've read it 5 times and I don't think I still understand what it's trying to say. A big bread money. Yep. There's something good happening there. Okay, well let's just copy and paste this bad boy into R and see what's going on. So this is, I'm just gonna maybe make a note here. This is exercise 2. Oh, I think I wrote a note for myself. I wrote, look at me being a good pen center. Split gives 2/3 to training. Stratify equals true ensures sample is roughly same percentage as population. I wrote a note to myself. Wow, good job, past me. Good job actually taking good coding notes. Okay, what are we doing today? We're going to create a confusion matrix. Is there any information that might be helpful to put in here? The relative equals true. I have no idea what the textbook is trying to tell me there. Maybe I should try relative equals false. And see what I get first. And then we can compare it to true. How's that? How does that sound? Okay. Oh, okay. So it's just going to give it to me as proportions. Got it, got it. Okay, so if I have relative equals false, I just get the counts. But if I have relative equals true, wait. Oh god. Cancel. Oh no, I did it bad. Jeez. I broke something. Okay, no. Here we go. So this is relative, and it gave me absolute confusion matrix? What? I just ran it like 100 times, that's all. Don't mind me. Shaky fingers. Okay, so it gives us information in terms of relative... Is it supposed to look like that? 0.92 of 1. 1 of 9.96? What? That doesn't look good. I guess some of these do look weird, I guess. Yeah, okay, so I guess it could be that the upper number is higher. Why would the numerator be higher than the denominator? What are we actually measuring here? The proportion of each class in the true and predicted. Oh. So is one of these percentages the true percent and one of them is the predicted percent? Normalized by row/column. Okay, brain, you can do this. Come on, brain. So where do they get 0.92 and where do they get 0.73? We do also have this tabularization here. Is that the same as the absolute? Yes. Which chapter? We're on chapter 3 so far. We're in like 3.5 or something like that. 3.5 of the Reese textbook. Hi, famished. I know my brain is like not. My brain isn't braining with like the numbers right now. There's something that looks weird, and I'm okay. So there's zeros and zeros, which probably means that there's zeros and zeros. This says 0.92 of 1. So does that mean that true? So 11 were predicted to be chemical. Okay, I need to write some stuff down here. I need to make this chart make sense to me. What does this 11 mean? 11 means, so this is the number of chemicals that were actually labeled chemical correctly. But there was one chemical that was predicted normal. Is that what this is saying? So 11 are correct. I know that these are correct, right? These are correct predictions. Anything that's not on the main diagonal is incorrect. So does this one mean that so there's a chemical that got predicted as normal? That's what I think that means. Everything else got predicted correctly? What? Yeah, I guess so, right? There's only one error in each there's only one error in the normal column and one error in the chemical column. So yeah, I think that might be the case. I think they must be thinking about this in terms of a row, right? So like these are the chemicals, and one of them got misclassified. Just reading through my introduction to the programming textbook and highlighting the important parts and having Gemini quiz me on the question. That's cool. Getting 100s on the quizzes, sweet. I don't remember them being I don't remember them being weird fractions. I think that's what's confusing me. So this must mean that 92%. Let's pull up a calculator. We have relatively straightforward numbers, so we should be able to put this together. So if there are 12 chemicals altogether, and 11 of them got correctly classified, that means that 11 out of 12 are correct, which is 92%. And 1 out of 12 is incorrect, which is 8%. So, 92%, 8%. What is this? 0.04. What is that? Column. Normalized by row / column. So, These are bugging me a little bit. So this must be looking at looking at the columns. It's saying that there were 26 normals, but we over predicted one of them, right? So we actually predicted 27 normals, so 26 out of 27. No, it's backwards, isn't it? So 27 out of 26 is what? It's like 1.04. There it is. 1.04. So the combination of these two things, that's fucky-wucky to my brain. That's super fucky-wucky to my brain. I get what they're trying to do, though. Right? Because there's really only 26 normals. We've over-predicted the normals. So we've basically captured all of the normals that we wanted, but we've over-predicted by 0.04. So that 0.04 they're putting here, and then the subtraction they're putting here by the looks of it. So they're basically normalizing it to 100. Okay, brain eventually worked. Great. The absolute confusion matrix is easier to interpret. Yeah, you don't say. The rows show the true class label, okay, and the columns show the predicted labels. The numbers represent the number... Well, let's actually... You know what we should do? We should double check the one in the textbook and see if it makes sense to you. So the weird one's going to be the chemical one, because it looks like 11 were true and predicted true. But we had 3 normal and 1 overt. So that's 11, 12, 13, 14,
Is that
15.
fixing Penn's brain? A complex equation indeed. We need a reprogramming algorithm. What's the first variable to adjust in this calculation? Time to calculate. So H cut away.
Wait, how many chemicals were there? $12. They're actually 12. So this is 15 by 12. I'm still unsure how they're normalizing the columns. How are they getting 73%? 11, maybe they're just doing column totals. 11, so I said 15, right? So 11 by 15. Haha! Okay, I see. Okay, so all they're doing is giving me percentages. They're not really fractions. The numerators, in quotations, are the row normalizations, and the denominators, in quotations, are the column normalizations. Okay, cool. Yeah, okay, so I think we got that. The relative confusion matrix looks a little more intimidating. You don't say! It only took me 20 minutes to figure it out. But the principle is the same. No, it's not. This time, instead of the number of cases for each combination of true class and predicted class, we have the proportion. The number before the slash is the proportion of the row in this column, and the number after the slash is the proportion of the column in this row. Yes. Correct. So confusion matrices help us understand which classes our model classifies well and which one it does worse at classifying. For example, based on this confusion matrix, it looks like our model struggles to distinguish healthy patients from chemically diabetic ones. Let's see if that's true. So so here's where it's having trouble, right? The biggest number of misclassified things was here at 3. Those are the people that are true normal, but it somehow labeled 3 of them as chemicals. So that must be what they're trying to say here, right? Based on this confusion, it looks like our model struggles to distinguish healthy patients from chemically diabetic ones. Yes. Hello, beautiful couch. How are you? I'm not sure if my brain will ever be fixed, but that's okay. As the performance metrics reported by Holdout CV depend so heavily on how much of the data we use as the training and test sets, I try to avoid... Wait. Oh, I see. So Reese is saying that they try to avoid this particular cross-validation unless my model is very expensive to train, and they generally prefer k-fold cross-validation. So that's interesting. That's implying that k-fold probably requires more computing power compared to holdout cross-validation. That's what I think they're implying. But that extra computing power maybe gives us something in return. The only real benefit of this method is that it's computationally less expensive than other forms of cross-validation. Right, okay, so that makes sense. So holdout cross-validation is computationally inexpensive. This can make it the only viable cross-validation method for computationally expensive algorithms. Gotcha. but the purpose of cross-validation is to get as accurate an estimation of model performance as possible, and holdout cross-validation may give you very different results each time you apply it, right? Because not all of the data is used in the training set and test set. Not all of the data is used in the training set and test set. Right. Some of it's put into training, some of it's put into test, and that's it. That's that. So k-fold cross-validation is the one that I'm kind of familiar with. So it's just basically setting up a bunch of holdout cross-validations is what it looks like to me, right? We give a certain percentage, and then it divides the data into those percentages several times. We maybe give it the value of k or something like that, or it determines the value of k somehow. And then it finds an amalgamation of these, I think, to get the model. So let's take a look. So in k-fold cross-validation, we randomly split the data into approximately equal-sized chunks called folds. Then we reserve one of the folds. As a test set, and use the remaining data as the training, just like in holdout. We pass the test set through the model and make a record of the relevant performing metrics. Now we use a different fold of the data as our test set and do the same thing. We continue until all of the folds have been used once as the test set. So this ensures that every piece of the data actually gets to be a part of the test set at some point. And then we get an average of the performance metric as an estimate of model performance. Cool. So nice visual, that makes a lot of sense. Hey Shark, how's it going? Yeah, Reese just got home from his walk, so he's probably just like laying by the door on the really cold tiles. This approach will typically give a more accurate estimate of model performance because every case appears in the test set once. And I guess everything appears in the training set at least once too. Probably multiple times. But yes, I see what they mean. Every piece of data should theoretically be a part of the test set at some point. And that must be the important thing. We are averaging the estimates over many runs, but we can improve this a little bit by using repeated k-fold cross-validation, where after the previous procedure we shuffle the data around and perform it again. For example, a commonly chosen value for k is 10. Depends on the size of the data, but a reasonable value for many data sets. This means we split the data into 10 nearly equal-sized chunks and perform the cross-validation. If we repeat this procedure 5 times, then we have a 10-fold cross-validation repeated 5 times. This is not the same as a 50-fold cross-validation. So they're saying a 10-fold cross-validation repeated 5 times is stronger than a 50-fold cross-validation? This, I see where this, like, I can see where increasing the number of folds could get problematic. Because if the number of folds is big, then these test set pieces become really, really small, right? So this is like a 1, 2, 3, 4, 5-fold, right? And a 50-fold would be 10 times smaller than this. So your test sets become really, really small. So it's better to keep your test sets bigger and just repeat through the k-fold more times. It's probably what it's probably the idea here. So if you have the computational power, it's usually preferred to use repeated k-fold cross-validation instead of ordinary k-fold. This is what we'll be using in many examples in the book. Cool. We perform k-fold cross-validation the same way as holdout. This time when we make our resampling description, we tell it we're going to use repeated k-fold cross-validation, rep CV. We tell it how many folds we want to split the data into. The default number of folds is 10, that's good to know, which is often a good choice, but I want to show you how you can explicitly control the splits. Next, we will tell the function that we want to repeat the tenfold cross-validation 50 times with the reps argument. This gives us 500 performance measures to average across. Cool. Again, we ask for the classes to be stratified among the folds. I wonder what Reese is barking at. Okay, so let's see how this is similar and different to relative gives normalized percentages across the column, row slash column totals. I see. So when we were doing the holdout method, we had to make a resampling description, and then we had to resample. So this is k folds cross validation. So we do the make resampling to script. The method is repeated repeated cross validation. Folds equals 10, reps equals 50, stratify equals true. So I'm just going to go ahead. I'm going to copy this information down here. And is there anything? So we needed the split. Do I need that here as well? No, I just need folds, because the folds is going to determine how the split got it. So folds. Well, I mean, folds determines the number of folds, but what's the easiest? How do I describe that in English? Folds is really the size of the test set chunks getting put back into the model, right? What?
It is
Tellus Matthew, really?
It looked like him.
Oh, I haven't seen Tellus Matthew since last year. Probably wanted to get Kleenex.
And water.
Kleenex and water.
I looked out the window and he was standing in the shade.
What shade? We don't have any shade.
Under the carport along the wall.
Oh, okay. Okay, I think that's the information I need there. I imagine these are gonna be similar, but let's copy paste this in and take a peek. So resample, learner equals KNN, right? That's what we have down here. Task equals diabetes task, so this is all the stuff we had already. Resampling equals K fold, rather than resampling equals holdout. And I see, so the resampling gets called from here. And then the measures, that's the same as up here, right? MMCE and accuracy. Cool. Did we put this one in K-fold? Let's put that into our memory bank. Let's run this and see what happens. Whoa, cool. You said it's nice out today? Nice, that's awesome. Yeah, today's like a little bit cloudy. I feel like if the clouds dissipate, it's going to be quite hot out today. You had a heat wave here, so it's been really hot the past couple of days. Hopefully you got to enjoy some of that heat. I love the heat. Sitting out in the sun. Now let's extract the average performance measures. K-fold CV, oh, I see. Okay, so this is going to get the information from the K-fold CV list. K-fold. So here it is, learner task, task description, Agger. These are aggregated results. Okay, so accuracy, the mean accuracy was about 89.5%. Right, or even if we round that up to 90, then it's about a 10% MMCE, which seems, that's pretty reasonable actually. Like, I know that like feels pretty high, but not too bad. So the model correctly classified 89.8 of cases on average, much lower than we predicted. The model rerun the resample function a few times and compare the average accuracy after each run. The estimate is much more stable, yeah. Then we use just a single holdout CV. That makes sense. We're usually only interested in the average performance measures, but you can access the performance measure from every iteration by running... Oh, that's fun. That's cool. I don't think we need to do that for what I want to learn, but that's interesting. Okay, so choosing the number of repeats. Your goal when cross-validating a model is to get as accurate and stable an estimate of model performance as possible. Broadly speaking, the more repeats you can do, the more accurate and stable these estimates will become. So this is just the law of large numbers, right? So the more I run this k-folds... The more k-folds I run, the more data points I get, and the more that average of data points is going to stabilize. I think that's just the law of large numbers. Especially if they're normally distributed, right? I don't know if they are. So maybe that's something the other textbooks can fill in a little bit. So there's definitely a little bit of like statistical background here in ensuring that this repeated process converges to something. Hey Ryan, how's it going? So yeah, so I think there's probably a little bit of like, there's some kind of like limiting structure happening here. Probably a statistical limiting structure like the law of large numbers would be my guess. So broadly speaking, the more repeats you do, the more accurate and stable these estimates will become. At some point, though, having more repeats won't improve the accuracy or stable. So how many repeats to perform? A sound approach is to choose a number of repeats that is computationally reasonable, run the process a few times, and see if the average performance estimate varies a lot. If not, great. If it does vary a lot, you should increase the number of repeats. Exercise 3. Define 2 new resampling descriptions. One that performs a 3-fold cross-validation repeated 5 times, and one that performs a 3-fold cross-validation 500 times. Use the resample function to cross-validate the canon algorithm using both of these resampling descriptions. Repeat the resampling 5 times from each method and see which one gives more stable results. I'm actually kind of curious to do this. And should we try to make a guess on which one will be more stable? So probably the 500 times, right? So we have 3-fold cross-validation repeated 5 times and 3-fold cross-validation repeated 500 times. Repeat the resampling. I see. So it wants me to repeat it 5 times and see which one is more stable. Yeah, the one doing 500 times should be more stable, I suppose. So let's call one of them k-fold. We'll call it 3-fold 5. Oh, I can't use a 3, can I? Fold 3 to 5. Fold 3 to 5. 3 folds. 5 reps. Bam. And then we'll do a fold 3 to 500. So 3, 500. Bam. And then we need to actually go through the procedure. And after that, we'll have to look at the aggregated results, right? So let me make sure that I have these. I don't think I need this anymore, so I can pop this up. So 3 to 5, so 3 folds, 5 reps. I called it fold 3 to 5. CV. So KNN, that's fine. Diabetes tax, that's fine. Resampling is fold 3 to 5. I still want these measures, so I think that's fine. And then when we're done, we'll look at the fold 3 to 5 CV aggregated results. Okay, let's see if I fucked it up or not. Now, I've already defined this thing, so I think I can just resample again. So the first one we got was like 88 and 11. Like 91 to 9. $89 to 11. Again, like 88 to 12. About 90 to 10. So all like fairly close, I guess. But they do differ by a couple of percentage points for sure. Like our accuracy like went from what, like 88 to like 90 something. This one might take a few moments. And that's to do 500 reps. That's a lot of reps. Like, this model's going to be jacked after doing 3 folds 500 times. So look at this. So 10 to 90 pretty much. I think what Reese is trying to imply here is if we do this again, it's probably going to stick really close to that, like, 90 to 10 breakdown. This pretty much, that's, like, almost identically the same. It literally went down by, like, 0.001. Okay, I'll do it one more time. Oh, this is cool. Okay, so now when we're doing our confusion matrix, because we've done a k-fold cross-validation, there's a lot more predictions happening. So we get a much more interesting, potentially interesting confusion matrix. Ah, interesting. Okay. I'm going to put that confusion matrix in there before exercise 3. Okay, what do we get? Yeah, look at that. That's pretty much the same to 3 decimal places as the last time we ran it. So that's pretty cool. So like we thought, the 500 repetitions makes these a little bit more accurate on subsequent runs. Cool. And here is our confusion matrix. Actually, I'm going to put that underneath the aggregated results. Like that. There's exercise 3, and bada boom. I am happy with that. So now we have a script that can run k-folds cross-validation for us. Hi, buddy. How are you? Hi. How was your walk? Did you have very good walks? Everyone's been wondering on stream where you are. Everyone's been wondering. They've wanted to see you. They did. Are you going to come here? wanna come say hi? You wanna come say hi? What are you doing? He's just putting his head on my lap. And he's not wanting to do anything other than that. You just want pats, eh? You just want attention. That's all you want, you big sucker. There you go. There you go. Oh, God. Is it not enough? Are you not satisfied? You need more pats? He would have been happy if I pat him for like the next hour. Okay, so this is the last cross-validation we get to look at. And it's called leave one out cross-validation. I've never heard of this cross-validation technique, so let's see what it looks like. So leave one out can be thought of as the extreme of k-fold. Instead of breaking the data into folds, we reserve a single observation as a test case. Train the model on the whole rest of the data, and then pass the test case through it and record the relevant performance metrics. So you're literally making the test set one item? That's ridiculous. Next we do the same thing, but select a different observation as the test case. Continue doing this until every observation has been used once as the test case. That's wild. So you literally just save one piece of data. You save one piece of data to use as the test case every single time, selecting a different one every single time until the whole data set has been used. Huh. Weird. And then take the average of the performance metrics. Okay. Because the test set is only a single observation, leave one out CV tends to give quite variable estimates of model performance, because we're really only looking at one single test case, right? Because the performance estimate of each iteration depends on correctly labeling that single test case. Right. But it can give less variable estimates of model performance than k-fold when your data set is small. It can give less variable estimates of model performance than k-fold when the data set is small. Okay, so when the data set's small, leave one out. Well, aren't we just essentially doing one-fold cross-validation in this case? And we would do it as many times as our data set is big. So that's kind of interesting. So when you have small data sets, it makes sense to do a one-fold cross-validation n times with n repetitions. It's also computationally less expensive, sure. Performing leave one out. So creating a resampling description for leave one out is just as simple as for holdout and k-fold. We specify leave one out CV. How is it different than a one-fold repetition n times? I guess that's my question. Do we really need to like go to the loo here?
Zeta, 17%. 5 equals 2, a delightful remainder in the mathematical dance. What's our next equation to explore? Time to calculate. So, kai, do, I.
He really struggles with Sakatoa, doesn't he? Really struggles. Because each case is used once as the test set, with all other data used as the training set, there's no need to repeat the procedure. Okay. I guess I'll put this into the script so that we have it when I go to put it into Discord for us. So this is the leave one out cross validation. Yeah, so they run it, so the resampling, learner KNN task, resampling equals LOO, same measures as before, we look at the aggregated totals. So there's nothing super surprising here.
Zeta, your sanity is paramount. Math is a friend in chaos. Now, what other numerical queries or calculations can we dive into? Time to calculate. S-O-A-Ko-To-O.
So if you run the rerun the cross-validation over and over, you'll find that for this model in data, the performance estimate is more variable than for k-folds, but less variable for the holdout. So it's somewhere in the middle. So, okay. So k-folds is the strongest, but is the strongest in the sense that it's less variable, but the highest computational cross-validation scheme we can use. It requires the most computational power. So we have the holdout, which requires the least amount of computational power, but is the most variable, and leave one out is somewhere in the middle. Now, I would be curious to know, it seems like leave one out is slightly better in variability compared to holdout, because every piece of data goes through the test set at some point, and it's an aggregate, right? Whereas holdout is just a single instance. At least leave one out is an aggregate measure, right? It's a mean measure of a bunch of different trials. So there's probably a couple reasons why it has a little bit better variability. Those would be my best guesses. Okay, if we want a confusion matrix, it's there. Cool. I don't know if there's really much to say here. So now you know how to apply 3 commonly used types of cross-validation. If we've cross-validated our model and are happy that it will perform well enough on unseen data, then we would train the model on all of the data available to us and use this to make... Okay, if we cross-validate our model and are happy that it will perform well enough on unseen data, then we would train the model on all of the data available to us and then use this to make future predictions. Yes. But I think we can still improve our KNN model. Remember how earlier we manually chose a value of 2 for k? Well, randomly picking a value of k isn't very clever, and there are much better ways we can find the optimal value. Cool. So we're going to get some information next about how to best choose k. Okay, I'm just kind of looking at time, and I'm unsure. Maybe I'll start reading 3.6. I don't really want to do more coding. I kind of want to save this script, upload it, and just make sure that I'm ready to head to work. But if we can read through Chapter 3 without really having to do too much coding, then let's do that. So machine learning models often have parameters associated with them. Yes. So it's a value that's estimated from the data and internal to the model, controls how it makes predictions. Sure. For example, the slope of a regression line. In the KNN algorithm, k is not a parameter because the algorithm doesn't estimate it from the data. Right. In fact, the KNN algorithm doesn't actually learn any parameters. Right. So k is called a hyperparameter, a variable or option that controls how a model makes predictions, but is not estimated from the data. As data scientists, we don't have to provide parameters to our models. We simply provide the data, and the algorithms learn the parameters. Like when we go to look at regression, I assume that it will do that. We do, however, need to provide whatever hyperparameters they require. Right. You'll see throughout this book that the different algorithms require and use different hyperparameters to control how they learn their models. So because k is a hyperparameter of the KNN algorithm, it can't be estimated by the algorithm. It's up to us to choose a value. So how do we figure out how to do that? So one way is to pick a sensible or default value that's worked on similar problems before. So using your past experiences to make it make sense. This option is a bad idea. Okay, you have no way of knowing whether the value of k you've chosen is the best one. Just because a value worked on other datasets doesn't mean it will perform well on this dataset. Okay, so don't just randomly guess. This is the choice of the lazy data scientist who doesn't care much about getting the most from their data. Wow, savage. Manually try a few different values and see which one gives you the best performance. This option is a bit better. The idea here is that you pick a few sensible values of k, build a model with each of them, and see which model performs the best. Are you still there, Famished? I have a doggo cam for you. This is better because you're more likely to find the best performing value of k, but you're still not guaranteed to find it, and doing this manually could be tedious and slow. Yeah, I could understand that. This is the choice of the data scientist who cares but doesn't really know what they're doing. Still pretty savage. Use a procedure called hyperparameter tuning to automate the selection process. This is the method we'll be using throughout the book. So how does changing the value of k impact performance? The values of k that are too low may start to model noise. For example, if we set k equals 1, then a healthy patient could be misclassified as chemically diabetic, because a single diabetic person is beside them, right? That's their nearest neighbor. Yep, that makes sense. In this situation, instead of just modeling the systematic differences between the classes, we're also modeling the noise and unpredictable variability. On the other hand, if we set k too high, a large number of dissimilar patients will be included in the vote, and the model will be insensitive to local differences, and will get overwhelmed. Like if there's a majority of cases in say, like chemically diabetic or whatever, then that's going to win every time we put a new piece of data in. Yeah. Okay, so tuning k to improve the model. Let's apply hyperparameter tuning to optimize the value of k. I think I want to do this the next time we get together, because I feel like there's going to be a little bit of coding to do here and interpretation of the output of the coding. Yeah, they're going to start doing like some of these plots. I do think... Should we make this a different script? Right, so what we're going to be doing is going back and playing around with this, right? This learner bit. So I think what I'm going to do is I'm going to end here. We're going to raid over into it. I think Academy's on. So let's go say hi to Academy. That's going to give me some time to upload the script to Discord for you so you guys can play around if you want. And I think what we need to do next time we get together on Friday is we'll create a new script that helps us do the hyper tuning of the parameters for k, and we'll just grab that as a script as well. So I'll try to do my best to kind of reorganize some stuff here so that the scripts are very kind of short and sweet. So we have like a script that deals with cross-validation, we have a script that deals with hyper-tuning, and then maybe we have an overall script that goes through the k and then procedure with k-fold cross-validation, or something like that. I haven't really decided how I want to break these scripts up, but I want to make these a little bit smaller and easier to read and follow. So let's make sure I do this right. Academy of Useless Ideas. Did I spell that right? Yes, great. You too, baby. Good to see you. Thanks for swinging by. We'll be back tomorrow afternoon. So we're back tomorrow afternoon with day 2 of Blueprints. Playing some video games there. And then a little bit later next week as well, we'll be back on Thursday night. Looking to do an Ocarina of Time crowd control Thursday night. And then back to machine learning next Friday at 11. So until then, have a fantastic rest of your weekend. Good to see you. And apologies that things were a little bit hectic on Friday for me. But still working through Chapter 3 of Reese. and some of the supplementary chapters from the other textbooks as well. I will post up the VODs after they get uploaded to YouTube in our Discord server so that you can follow along if you've missed something. And until next time, until Friday, have a fantastic day, and we'll talk to you guys later. Bye!